In this video, I want to map a volcanic feature, and in particular, we're going to be mapping part of Olympus Mons. So on Mars, you guys have seen the chain of volcanoes Tharsis Mons down here. And if we were to move to the northwest of that, we would see Olympus Mons. So these are all shield volcanoes, but this is the biggest, and it's the biggest one in our solar system. So what we're going to be focusing on within Olympus Mons is just this top part right here, and that's called the caldera. If we were to make a topographic profile going across the caldera, we would move from, let's say, point A to B. We would go down into that caldera across. There's a little bit of a lower part, and then it comes back up, and we've got a wall. This little part down in the topography is associated with this feature right here, which is an impact crater. We'll look at imagery in a little bit. Just to remind you of what a caldera is, if you could imagine taking a big bowl and filling it with flour, and sticking a balloon, and it doesn't have to be inflated, sticking a balloon in the hole, and then having some kind of straw out here that you could blow into. So let's say that we can blow into that straw. This is air. Let's say we can blow into that straw and fill up this balloon. As that balloon fills up with air, this is going to mound up. That flour is going to mound up. And that's kind of what happens before there's a volcanic eruption. Over time, the magma chamber is going to build. It's going to get bigger. This mound is going to get bigger. And then when the magma chamber empties, when it makes it to the surface and it actually extrudes that lava onto the surface, this now becomes emptier. So let's say some of this magma empties out, and now this area is hollow. Well, hollow space below ground doesn't do a good job of supporting the rock above it. So that's going to potentially collapse, and when it collapses, the top part is going to fall back in. So we would have sides that are still pretty supported, but we have this middle part that's less supported. So in profile, we'd go up our hill, some of which is new material. Then we've got this kind of collapse pit in the middle that's caused by collapse around this part that's emptied out. And we would still have a tube going to the magma chamber, but the magma chamber would be less full than it was before. Now, over time, you're going to have more eruptions, or you could have more eruptions. And every time you have an eruption, and let's say we empty out this part of the magma chamber, now we're going to collapse this additional part of that rock unit. So now our topographic profile of this volcano might look something like this. And so these are reflecting more emptying, and these are reflecting places that just haven't emptied over and over again. If you're interested, there's a great USGS video, and I'll include it in the description of this video, that shows this flower example of the flower lifting up and then the middle of the flower kind of collapsing out when you let the air out of the balloon. So if we look up at this topographic profile again going across Olympus Mons, we have the walls of the caldera, and then we have multiple steps or levels of that caldera. And again, this is impact crater, so not really part of the volcano. This is a 3D DEM, or digital elevation model. It's a image draped over that, or the image is expressed with elevation through a DEM. And you can see these walls of the caldera. They're kind of streaky looking. And that's because they're due to that collapse. So this part has basically collapsed back in. Okay. The other feature that you might notice that look familiar are these linear kind of squiggly landforms. And you might recognize those from previous mapping videos as being thrust faults or thrust fault related landforms. So the reason why we get those is thrust faults form when you need to shorten the terrain that you're starting with. So if we have initially, that's kind of minimum topography, right? But let's say we have a mound to begin with, okay? If we have this mound to begin with, and we unfolded that topography, we took this arc and we unfolded it, we would get this really long length of rock. So when that long length of rock collapses into this amount of surface area, this, even if we, flattened it out, it's still shorter than the unit previously had been. So we're basically taking this amount of material and we're putting it on top of this shorter place, and so you're going to have overlapping material, you're going to have folding. So imagine icing a cake, but your cake is a really small cake. So let's say this is the cake we want to ice, and we have a massive thing of icing, okay? And we're told we can only ice the top of the cake. Well, we're going to end up having overlapping units of icing because we're just going to keep stacking icing on top of the cake. We've got a big amount of material that needs to color a relatively small space. So the only way to do that is to stack it, is to shorten it and fold it. And that's why we're seeing these features in this area. So in terms of the caldera, we're going to have differences in topography that are caused by eruptions that have happened over time. And we're going to want to let that process guide our definition of units, at least for this particular class. Okay, so what we've got here is a CTX image, so context camera imagery, and then a context camera DEM. And this DEM, I think, was made by the University of Hawaii. I want to make sure I attribute it properly, so I'll do that in the comments as well. We've got dark blues that indicate deeper parts of the caldera, and then this is the outer part. This is no longer the caldera, this light part. This is the edge of the volcano that didn't collapse, and then we've got the impact crater. So over here you'll see A to B. A would be up here, B would be down here in terms of topography, and the A to B on that side corresponds with A to B over here. So this A going down into B, we can see that deep caldera right there, and the deep one corresponds with this one. Okay, so if I were going to map this, I might choose to map deep calderas as one area. I might choose to map this as a deep caldera over here. I'm going to dash my boundaries once I'm certain about them. And notice that I haven't included caldera walls. I'm going to have those be a separate unit because those are really surfaces of collapse. They're kind of separate features. And I'm going to group all caldera walls into one unit. They're all kind of representing, even if it's a different age, they're representing the same process. I think those are probably closer to being thrust faults. I'm still going to put a boundary unit here. Okay, so we've got caldera walls. We have these deep calderas, shallow caldera. Here's another caldera wall. And then over here, you can map the impact crater separately if you want to. I'm probably just going to leave it as an outside unit. So let me go ahead and start coloring. So for me, deep calderas are kind of a separate unit because they represent additional phases of volcanism and release of magma as lava to the surface. So I'm going to color deep calderas as one unit, shallower calderas as another unit. And you could even divide this into 3 different depths. You could have, this area that I'm coloring in as orange, you could have that as kind of a mid unit if you wanted to. I'm just, for the sake of time, I'm going to keep it all as one and say that they are deep and then shallower calderas as 2 separate units. Caldera walls, doing purple. And my outer area, I'm going to do in brown. This is also caldera wall right here. Okay, so I have 4 units. Let's go ahead and define these units. We'll start with there's outer unit. This one, this unit. Okay. And we're dividing based on processes, but also on what they look like. So this is the deep caldera. This is caldera wall. This is younger. Actually, younger is kind of an interpretation. We'll say shallower caldera. And then the brown one we can say is outer unit. So now for the description, calderas are, they're roughly circular. They are, and we have exact values for depth because we have the DEM. So this we're looking at around 17 kilometers deep in center of volcano. And then our interpretation is that they are calderas formed by additional magma releases and collapses. We could also say that they look roughly smooth and that they have thrust fault related landforms on them. The caldera wall is a smooth, streaky change in elevation unit around the calderas. Interpretation is there, the collapsed surface walls. Shallower caldera maybe represent, and I didn't mean younger earlier, I meant the circular features. They are between, let's say, 16 kilometers depth and 20, let's see, maybe 19 kilometers. These are, I shouldn't say depth, that's actually elevation. So 16 being deeper, 19 being higher, 19 kilometers elevation, center of volcano, smooth with thrust fault related landforms. And we can interpret them to be earlier, maybe more massive eruption features. And then the outer part is the volcano surface still supported. That's our interpretation. It is higher elevation. It looks smoother. No thrust fault related landforms. A few superposing craters. And it's got a change in tone. So changes or variable tone. And that could be due to eruption. So that bright spot that you're seeing on here, you know, that could be a lava flow. Maybe related to lava flow. And then the data types used, I just always like to list them. The data types would be the DEM and the CTX image. All right. Thanks for watching. Bye.